So derivative of x squared plus kx minus 3 is 2x plus k. Imagine this was x squared plus 5x. Then the derivative will be 2x plus 5. So same process, 2x, x squared plus kx will be 2x plus k. Right. Next up, 3x plus b. 3x becomes 3. B doesn't go to 1. B is a constant. B will go to 0. It's 2x plus k. No, 3. Okay. We still have to replace every x with 1 because we know that that's the where they're going to meet. Should be able to get it down to a point where we can solve for k and b with 2 equations. So this piece is still unresolved. We can't solve for k or b with 2 variables, with 2 unknown constants. But if I should be able to solve for k here, once I replace x with 1. So 2 plus k equals 3, k equals 1. So I should be able to use that information to put into my second or to my other equation and solve for my other missing value. Okay, replace k with 1, solve for b. So there we have it. We have our unknown constant solved. And the strategy there is set the equations equal because the graph is connected. They use the word continuous. And we know that the graph is going to be a smooth transition from one graph to the next. It's going to be they're going to have to share the same slope. And because they share the same slope, slope is related to the derivative. We find their derivatives, set them equal to each other as well. Then we have two equations to help each other to solve for k and solve for b. Okay, take a look at number 9. Y equals e to the kx, then find d5y over dx5. What do you think that notation means? The derivative. Yeah. It feels like, wow, that's going to take a long time to do. But after you find the first derivative, you should be able to discover a pattern and then just repeat that pattern over and over again. So I'll find the first derivative and then see if you can decide what's going to take to get down to the fifth derivative. So y equals kx, e to the kx, sorry. K, again, is a constant. So imagine this is e to the 3x. Right? Treat that the same way. What's the derivative of e to the kx? Times k, which is k e to the kx. And k is just going to be a coefficient. There's no need for a product rule. So repeat that process again. Find the second derivative. The k stays. E to the u becomes e to the u times u prime. What does that clean up to be? How many k's do you see? K squared, yeah. So hopefully you see a pattern occurring, right? So if we see the pattern, we can jump to the fifth derivative, but if not, we can do this a couple more times here. What's going to happen each time we find the derivative? What's going to show up? Another what? Another k, yeah. So third derivative will be k cubed e to the kx. Fourth derivative, k to the fourth e to the kx, right? Each time we just are going to produce another coefficient to tack on to the k's that we already accumulated. Okay. Next up, number 10. Consider the function f of x equals 6x over a plus x cubed, for which f prime is 0 equals 3. Find the value of a. So we're going to find f prime. After we find the derivative, we'll replace every x with 0. We'll replace the slope with 3, and then we should be able to solve for a. Remember, a is just a constant, so the way you treat a is the way you treat 2 or 3 or 5. Now, if I want to find f prime of x to get to this stage, this level, so I can use my order pair at the derivative level, what do we have to go through to find the derivative? Quotient rule. Okay, so try that. Apply quotient rule. Again, a is a constant, so you want to treat it the way you would treat a constant. All right, so this is what I got after quotient rule. I'll treat the numerator as the f, denominator as the g. So f prime g minus f g prime all over g squared. So 6x becomes 6. G stays as a plus x cubed. F stays as 6x. G prime becomes 3x squared. The a disappears from here because we treat a like a constant. All over denominator squared. A plus x cubed quantity squared. Any questions here to get to f prime? Right, so now we can replace all the x's with 0, and then replace the f prime variable with 3. And we should be able to then maybe cross multiply and then isolate and solve for a. So every x gets replaced with 3. The f prime, the derivative variable, gets replaced with 3. X is 0, y prime is 3. So this cleans up. 6a minus this whole thing wipes out to 0. So it's just 6a over a squared. If I cross multiply here, I get 3a squared equals 6a. Bring everything over to one side, factor out the a, 3a times a minus 2. There's actually two potential solutions. A could be equal to 0. A could also equal to 2. Okay, next page. Number 11 is meant to be a related rates problem. So each time we come across h, we have to attach a dh dt. Each time we come across b's variable, we attach db dt. So that's the thing with related rates. Every variable gets impacted by time. Okay, so we're going to find derivative like we normally would. H cubed will simply become 3h squared, but we need to attach dh dt since time is impacting every variable. Now this side, what rule do we have to go through to find the derivative for this setup? Chain rule, yeah. Okay, so we take turns with each derivative. The parentheses squared becomes 2 parentheses to the first power times inside's derivative. 4 goes away. Negative 2b becomes what? Negative 2. Now we're still doing related rates here. So negative 2 what? dB dt. Yeah. Okay, so let's see what we have. So we can plug in and find the variable that we're looking for. So we know that dB/dt is 3. So we can use that information. H is 4. We can use that information. And we're looking for dH/dt, which is the unknown. So if I can replace dB/dt with 3, I can replace H with 4. I'm solving for dH/dt, but there's still something that's sticking out that we have to still find. B, yeah, because they don't give B to us. So how can I find the value for B if they don't give that value to us? Okay, use the first equation and plug in what? Plug in 4 for H, right? So this requires we have to do some additional hunting for that variable. So H cubed equals 4 minus 2B squared. 4 cubed equals 4 minus 2B squared. 64 equals take the square root. Plus or minus shows up. Now we know we can ignore this -8 because eventually it's going to be -8 minus 4. Well, let's see. Let's do them separately here because, well, ultimately B value can't be a negative value because they say that positive variables B and H. So let's see what happens here. 8 equals 4 minus 2B. And then we also have -8 equals 4 minus 2B. Meanwhile, I have -12 equals -2B. So B equals 6. And between -2 and 6, we're going to choose the 6 since they said at the beginning that B value can't be negative. Okay, so H is 6. Sorry, B is 6. And now we can go back to our original equation and put everything in and solve for what we're looking for. 3 squared. Two times B, 2 times 6 is 12. Clean all this up here. 2 times -8 times -6. All right, final step, divide both sides by 48, dH/dt. 6 over 48, which is 2. Number 12 is also another related rates. Anytime we see something over dt, we know that we're going to have to go through related rates here. So number 12. So each time we come across z or x or y's derivative, we need to produce dz dt, dx dt, dy dt. But if you look at number 12 here, what else do we have to make sure we involve as part of our derivative process? Something about this xy squared here. We got to go through what? Product rule. Yeah. All right, try that. So got to go through product rule here with x and y squared. So we go through our process here. Z becomes dz dt. And then we do f prime g plus fg prime. So x becomes dx dt. We keep the y squared back to f, which is x. And then y squared becomes 2y dy dt. We have z to plug in. We have y to plug in. We have dx dt and dy dt. But we're still missing x. So because we're missing x, we have to kind of go back to our original equation, plug 3 and 1/2 in, and then have to gather that information before we can truly plug in and solve. But if I plug in 3 in for z and 1/2 in for y squared, I get 3 equals 1/4 x. Cross multiply, x equals 12. So now I can plug in all the values can now be plugged in, and I can solve for my missing variable, dc dt. Okay, so next up, number 13 is linear approximations. So multiple step process, but really we're just going to focus on finding our tangent line equation. If I can find the tangent line equation, then that's really the bulk of the work. The last piece is just putting in that decimal. So to find the tangent line equation, we first have to find the order pair at 0. So we're going to build our tangent line at our anchor point, which is at 0. So we'll find the order pair at 0. We can find the derivative and then plug in 0 to get the slope and then point slope form. And then at the very, very end, then we can plug in that 0.08. But at the beginning, we ignore that 0.08. We're just focused on the equation, the curve and the point to get that tangent line equation up and running. So All right, so imagine this is the only information given to you. Then let's go ahead and find the ordered pair, find the derivative, plug in the x to get the slope, point slope form, and then at the very end we can decide what to do with that 0.08. So 3 plus e to the 0 is 1, 3 plus 1 is 4, square root of 4 is 2, so there's our ordered pair. Derivative, inside, outside, we got to go through chain rule. Inside's derivative, 3 goes away, e to the x is just e to the x. Do some cleanup, and then plug in 0 to find the slope. Okay, so we have enough information to build our tangent line. We have our ordered pair. We have our slope, point slope form. So I'm just going to move that 2 over. And then once we get our tangent line equation, then the final step is just plug in that 0.08. That's where the approximation comes in. So the linear is what we did here, and then the approximation is putting in that decimal in. Okay, 14. This is just interpreting function and derivative notation here. So function c of x gives the dollar cost of digging a hole x feet deep. So c of 20 equals 140. This is just basically at the function level here. Means that a hole this x feet deep. So x is the input, and the cost is the result based off of how deep that hole is. C prime of 20 equals 5. So that means, when the hole is 20 feet deep, there's a rate at which the cost is changing. But it's positive, so we know that the cost of digging is increasing at a rate of $5 per foot. Okay, we have some time here. I think we should be able to maybe get a good chunk of page 3 done. And that way, sorry, good chunk of page 5 done. And that way, on Monday, we should have to take the quiz and finish off the last page. All right, let f of x be given. The graph of f has a relative max at 0, 1, and an inflection point at x equals 1. The values of a and b are. So it doesn't feel like we have enough information to get all this data, but we actually do. If a function has a relative max at 0, 1, what level will allow us to get to relative max? Derivative, yeah. So relative max, we're going to find f prime. And if I want to find a relative maximum, that's usually when what happens? What do I do after I find f prime? Before I get to relative max, I first have to get to critical point, right? So how do I find a critical point? All right, think about first derivative test. What happens after you find f prime? Yeah, set f prime equal to 0. So that's, we're going to take those steps, right? We're going to set f prime equal to 0. And that will at least get to the level where we can make some more progress with what information they have. And then there's an inflection point when x equals 1. So again, inflection point comes from the second derivative, same process. We'll set the second derivative equal to 0 and then see what that gets us. Okay, let's find f prime, and then we can kind of go back and forth to see what we need. Remember, a and b are just constants, so we'll treat them like constants. X to the fourth becomes 4x cubed. Ax squared becomes what? 2ax. And then the b, 0. Okay. And then we also have information involving the second derivative, so we can also take it to that level. 12x squared plus 2a. Okay, we know that we can set f prime equal to 0. Some of these may not get us to anything that we need, but we know we can at least get to these places, 12x squared plus 2a. We know to get to point of inflection, we have to set the second derivative equal to 0. I'm sorry. I shouldn't found the derivative again. I just should be able to set this equal to 0 directly. I already found the derivative. Sorry, 4x cubed plus 2ax. All right, so they gave us an order pair. So I'm going to take that order pair and put it into the function because this is at the order pair level, right? 0, 1 is at the order pair level. So let's just see what that gets us. So I'll plug in 1 in for y and 0 in for x. So this wipes out a lot of information for us. We can get to our b value just by putting in that order pair 0, 1 into the function. So b is equal to 1. We have an inflection point when x is equal to 1. So that's going to occur at this moment. So I can take that x equals 1, put it into the second derivative because I know that at x equals 1, that's when f double prime is equal to 0, right? So all this is connected. So a is equal to -6. All right, so we have b equals 1, a equals -6, and we have everything that we need, right? Okay, last set of problems here. We're looking at the f prime graph, and we want to be able to interpret accordingly here. Let's just see if we can practice creating our slope and concavity sign lines since we're going to sketch their graphs below. So as a reminder, if we're looking at an f prime graph, anything above the x-axis is going to be where my original graph is going to experience positive slope. Anything below the x-axis is where my original graph will experience negative slope. So let me create my f prime sign line. Right? What's my one critical point on my f prime sign line? Okay, yeah, when slope is 0. Between 0 and k, above the x-axis means positive slope. Between k and m, below the x-axis means negative slope. So my actual graph is going to do this. It's going to rise to some y value at x equals k, and it's going to fall after that. All right, f double prime is the curvature and what two critical points do we use if we're looking at if we're trying to find potential points of inflection off the f prime graph? The max and mins, right? So J is our point of inflection, and then another one occurs at L. Now, if we're looking at if we're trying to determine concavity, now we look at the slope. Positive slope on the f prime graph means concave what? Concave up, positive slope, concave up, yeah. Negative slope on my f prime graph is concave down, and then positive slope is concave up. Okay, where does the absolute minimum occur? Yeah, so I don't know if this is something that we can, we'll get back to next semester we'll learn more about this here. But I think we can figure out where the absolute max occurs. If the graph is rising and falling after that, then the max has to occur at K because the graph is not going to rise up again on either side. So absolute max occurs at x equals K since our function is increasing from 0 to K and decreasing after that. So there's only a rise and a fall. So that maximum is going to end up being the absolute maximum. Okay, now. All right, let's do the last two parts here. Sketch the graph, potential graph of f, given that f of 0 equals -2. So they gave us an anchor point for us to start with, 0, -2. And our strategy is we're just going to follow what the slope graph tells us. It may not be perfect, but at least we can get the basic movement of our graph, and then we can go back and give it more detail in terms of curvature. So we know our graph is going to rise to some y value at K. We don't know how high that y value is, but I'm just going to go to some point here. And then from K to M, my graph is just going to fall. All right. So my graph should always look like what the arrows are telling me. Okay, I know there's a point of inflection at J. So somewhere between my max, my increase, I'm going to target a J. And then K is going to have to occur sometime after K. So I'll target a point somewhere here. And then I'm just going to go back and give it the curvature in each subinterval here. So from 0 to J, concave up. From J to K, sorry, J to L, concave down. And then from L to M, concave up. Now, it's concave up, but it's not going to be a full concave up. It needs to stay decreasing. So it's only going to have a concave up shape in the sense that it's only going to show a portion of it. It's going to have to kind of follow along this path. We've already set out the path. We can't create a new path. Okay, next up, we're going to create a second derivative graph. Second derivative graph is only relying on the second derivative sine line. And we know that J and L are points of inflection. They're going to land on the x-axis. Anything above the x-axis is concave up. Anything below is concave down. And we're just going to thread our graph through these points. The graph is not necessarily going to look like these shapes. So, but above means, concave up means when you start above. And then between J and L, we're going to have to step below since it's concave down, but it's going to have to come back up again. And then after L, it's going to go back up. It's going to be in the concave up region. So on Monday, when you guys come in, we're going to just have you guys look over your notes for about 10 minutes or so. And then we'll take the quiz. And then we'll finish the last page. And I'll walk around and I'll check off your pages 3 through 6. Okay. Now, as you guys come up and get your phones, I have another practice blank sheet if you want to pick one up. If you're good, you don't have to pick one up, but it's just there in case you feel like you want some additional practice. All right, come get your phone. Some beer money. Can I go ahead and show you? Sure. So 3, 4, 5. I just went ahead and pushed that. All right, great. Thank you. Thank you.
Show you number 2.
What are you using? What kind of?
Oh, I used to go on it. Oh. No, I'm sure. I didn't think it would be. Wait, no, you'll be that.
Please. Yes.
Maybe, so I finished my during 7 years ago.
Okay, sounds good.
Else the ones. Whatever. Yeah. Oh my goodness.
Have a great weekend, guys. See you Monday. Thanks. Thank you.
You know what? I talked to the boy. You just have a roster. I'm like, I'll never, like, you went this. Yeah. Very true. That was. Yeah.